I'm Philip. You probably know me. If you don't, I used to work with the great people at FreeHack at FSU. Now I work at SAS as an industry consultant in GIS. Don't worry, this talk has nothing to do with selling software or products or anything. This has everything to do with some stuff that I've been thinking about recently, and hopefully it will make sense to everybody on the call. We'll see. So yeah, solution space versus problem space. First off, let's see. Is my slide going to change? There it goes. Okay. Why is this in the way all the time? All right, so yeah, here's the kind of the roadmap of what my talk is. If it looks kind of, I don't know, these are all the things we're going to be talking about. So if you get bored, you'll know that, hey, we're at causal inference. There's only one more thing to worry about, and then I can get out of this room. But otherwise, hopefully it'll kind of make sense. Confessing sins is the one that I'm excited about, but we'll get there. So yeah, what am I doing first? All right. Okay, Param texted me yesterday and he was like, Phil, are you giving another presentation? And I was like, yeah, I've given, and he was like, how many have you done? So I went back and I realized that these are slides from SHRUG 2016, which is now, oh my God, 4 years ago, in which I hope I am not repeating myself, but this is almost, it's the same thought, but hopefully now I have much better ideas about what analyzing data means. So here I was complaining about how people visualize data and then analyze those results. When what people should be doing is analyzing data and visualizing the results. Well, today I'm basically going to be revisiting this topic, but I have a much more nuanced perspective, I would say, on what analyzing data means or how we should analyze data. And it all has to do with solution space versus problem space. This is an odd concept, so I wanted to like define it first or tell you where it came across. I was reading this book called The Book of Pages because, well, you know, it's coronavirus, and so I ordered stuff off of Amazon. So on page 8, this is the kind of thing that's in it. I wanted to read this because this kind of really struck me when I was thinking about visualizing data, what maps are good for and what they're not good for. On page 8, it's this little monk named Jiriki, and he goes to the city, and at this point he's in the airport, and he says, maps are just snapshots of the destination problem. I mean, you look at one to see what obstacles are in the way of your destination, and you plan ways to overcome them. But ordinary maps are maps of real space. They tell you very little that you couldn't see for yourself if it wasn't for the limitations of human eyesight. And they don't actively help you find a solution. It's not interesting to be shown that the destination is very close to here if there's no direct path between the two. And he goes on to talk about how there's what I've called solution space. He's at the airport, and he notes how when you're in an airport, in a sense, you know, the LA airport or the airport in Sydney, Australia, is almost in a way closer to you than, say, places that are, you know, they're physically closer to you, but in the sense of where you're going, in the sense of problem space, or in the sense of destinations, they're actually further away. They're actually harder. It's harder to get to some places than others when you're at an airport, and it has to do with where you are. So I don't know, there's this idea that it really kind of struck me. I started thinking about it because I feel this way when I go to an airport. You see the boards with all the flights, and I'm like, wow, I could go to like Singapore right now if I had $8,000 or whatever. But so yeah, I wanted to describe, like, or I wanted to kind of define this idea in terms of maps, in terms of data, in terms of what we do in GIS or in data science or spatial data analysis. And I kind of had these, they're kind of loose terms, but so here it goes. When a map displays data that led you to ask your question, it's mapping the problem space. When a map displays information that leads you to answer your question, it's mapping the solution space. So and actually I think examples help a lot here. So here's an example of the problem space. This is an actual map of what the London Underground looks like in the center of the city. So the Tower Hill, that's where the Tower of London is. This is the problem space. This is showing you all the information that you already know about the London Underground. It's a complicated, messy place where it's confusing where to turn and how to get places. The solution space is this. It was like given. I think it was like one of the top 3 designs in the last 10 years. I can't remember what it was, but this solution space built by an engineer shows you, it kind of answers the questions. It gives you a very clear idea of how to answer the questions you had to go. When you look at this map, you're not so worried about the complexity of it. What you begin to know, and once you start knowing how to read the information, you begin to see all the different possible answers to the questions you had. In fact, it tells you even more information than what you may have been thinking when you saw the complex underground system previously. There's another one. This is from Kayak. It's the problem space. It's how these are flight costs from London. So if you're flying from London, these are the prices to go to various cities. And you can see some of the cities have been flagged, and actually the red and green dots have to do with COVID restrictions. But you can see there's a lot of information that you can't see. And it's also not clear where are the spots that are cheapest to get to. How far could I get from London for, say, the cheapest amount? And I found this map in my GIS book from school. It's called the Globe Recon. It's from 1992, so don't pay attention to any of the pounds or any of the costs. But this actually displays exactly the answers to the question, how far could I get for, X amount of money, for 200 pounds, say. And what is interesting about this, to me at least, is that it shows you surprising things. It shows you places in the solution space that you never would have thought. So for instance, I know it may be hard to see on your screen, but it's actually in terms of money, in terms of the cost it would take to get from London to somewhere else in the world, to get to the Shetland Islands, which is just north of Scotland, right? It's very, very close to London. It's actually, the Shetlands are actually farther away than Miami. Or, you have these other you have these weird things where I think, LA is actually closer to London in terms of money spent than is Madrid, Spain. At least it was in 1992. I don't quote these prices right now. So here, these are examples of problem space and solution space, how mapping answers to your questions are different than simply mapping the data that caused the questions to be asked in the first place. I hope that makes sense. All right, so the second part, COVID-19 dashboards and Thanksgiving. So here was my question. I wanted to kind of frame all of this in a very relevant, in a relevant setting. Here was my question. This is literally a question I've had for a couple of weeks now. What is my general risk for transmitting or contracting COVID-19 if I visit my family next week, like literally next week for Thanksgiving? It'll be the first time my family's seen each other for like 3 or 4 years. I'm almost obligated to go. And I just want to know, what's the general risk? Like, am I putting my elderly parents at risk? My little baby nephew? Like, how? I know that there are different risks going on in the country. I know that my family practice, they wear masks, they stay away, they socially distance. I do the same. We're both in areas that have relatively low infections at the point. So given all that information, I just wanted to know, what's my general risk? So I went to the de facto spot for GIS and spatial and COVID data, the Johns Hopkins dashboard. And this is all of the data I was able to find. It was so frustrating to me. So here, at the top left is the new cases by population. That's Tennessee. That's Florida, and then Tennessee, where my parents live. My sister actually lives pretty close by. To the left, we're all in this ugly beige color. And really, I looked at this information. I looked at all of this data, and I realized that it's just telling me what I already knew. It's telling me this is the information I already knew, which made me ask the questions about my general risk. And it's not telling me, this is problem space. It's not solution space. It's not leading me to answer the questions that I had. It's not demonstrating the various things that will influence my decision about whether to go. It's just telling me all the stuff that made me nervous enough to ask the question that I wanted. I hope that makes it. This is really weird, not being able to see anybody. Yeah, and you can tell that the dashboard wants to give you some sort of information. It's clearly full of data. I'm just not sure what questions this data is primed to answer. Like, I don't care how many healthcare. I know maybe I'm asking the wrong questions of this dashboard, but the problem is I don't think this dashboard is very different from all other dashboards. And I was just struck by how little I was able to answer, even about basic questions here in Tallahassee. Like, I want to go back climbing at the rock gym. I know they've met all of these requirements. I know they have stringent, temperature checks and all kinds of things. When can I go back? When is it safe? When are the risks for me low enough that I might be willing to put up with them? And none of this information answers that question. It speaks to me in no way whatsoever. Anyway, this might just be a personal thing. I don't know. I was just struck. And especially after thinking about problem space and solution space, I was thinking, this is problem space. So how could you model a solution space? And again, I said I've kind of moved from the world of GIS to the world of data science and machine learning. And this is definitely the model, the process that they go through. So you begin with exploratory data analysis. You begin to look at all of the information you have. You find where you have gaps. You find what you may need to continue gathering. But after that, you build a model. You set up some sort of equation or representation of the problem that you're trying to solve. And you plug the data in, and then you test it. And then you're in this loop where you build a model, you test it. You find where the model fails to account for things. And you change the model and you test it again. And you go back and forth. And I started thinking that in a way, this process is very much delineating the space, the gap between problem space and solution space. Problem space has its place. Problem space may be a bad way to describe it, just because it's not necessary. It's describing the problem. Like in the book of pages, you look at a map, you look at the problem space to see what obstacles are in the way of your destination, and you plan ways to overcome them. The problem is that when you never move from that problem space to a solution space, when you don't take the step and begin to kind of grapple with the very difficult, I'm not going to say it's easy, the very difficult challenge of creating models that could answer the questions that are important to us, questions about general risk. I mean, again, I'm posing all of this in terms of COVID just because it's so salient right now, but hopefully you can see how this applies to lots of other things. In another way, this is let's see. Yeah, you can think of problem space as the inputs to our analysis, to our models, and the solution space is the outcomes. And what I would argue, kind of what I did in the abstract, is that when our dashboards, some dashboards are only mapping the problem space. They're only mapping the inputs to our problems. They're not mapping any potential outcomes, any potential useful solutions to the questions we have. So I want to talk about how could we do that? How could we model a solution space using spatial data? Because we're GIS, and we've all been told that spatial data is special. So certainly, how could we use spatial data to model a solution space? All right, this is the confessing seat. You're a third of the way through, or halfway through by now. Confessing sins. This is the spot where I have to say, well, it's kind of a nuanced thing. When considered as a data type, actually spatial data is not special. It's just simply not a special, if you think spatial is special because it needs coordinate systems or because it's really complex or takes a lot of space, none of those things are necessarily true. They may have been a while ago, but not so much anymore. You have to excuse, he's an Italian, so excuse his English, but Alessandro Ferrieri, who developed SpatialLite, an open source spatial database that sits on top of SQLite, said spatial data processing simply is a branch in computing between many others, and spatial data are too much strategic and pervasive to be confined to niche applications. I should have said that with an Italian accent, but I would probably offend people. So anyway, you get the idea that spatial data, well, yeah, here's some examples that I came up with of how spatial data isn't all that special when you just think of it as a data type. These come from the book, he's got like the best last name ever, Michael Warboys. It sounds like you're reading like a Mad Max novel while you're reading about like archery indexing and stuff. It's very odd. Anyway, you can think all raster data can be translated to vector data, which can be stored as a table in a database. It's at the end of the day, it's all a table. You might think, look, spatial queries, we saw this yesterday actually with Seth Bassett's talk on spatial SQL, right? Spatial queries are computationally expensive SQL queries. That's all they are. They actually, if you read this GIS Computing Perspective book, you can read how a database uses indexes to just find numeric values that fall within certain ranges, and that's what a buffer is. That's what an intersect is. It's just set theory and math. And then I started thinking, I was like, wow, even site selection can just be thought of as a long where clause. Select all the places where the slope is this and the aspect is this, and there's certain other information that meet these criteria. It's just one giant SQL query. So yes, if you only think of spatial data as a data type, it's not special. However, I suppose I should recant. If you want to ask, how is spatial data special? I think spatial data is special. I swear I'll stop saying that in a minute, because it's encoded with the distance to all other spatial data. I think I was thinking about this, and I think it actually is kind of special in a way that we don't realize. You realize that like every piece of spatial data is inherently related to every other piece of data that has space to it, whether you know it, right? There are like, I just listened to a book on spies. There's a KGB file somewhere in Moscow with spatial data in it. And if you knew what that data was, your data is related to it in measurements of distance, right? The measurements of like the Hadron Collider, all of those particles are inherently related to your spatial data because they just have a distance from their particle to your spatial data. All spatial data is linked to all other spatial data, and I think that's actually what makes it special. And so, of course, you can't get away from it. Why is this special? Why is this important? How can we use it? Well, because everything's related to everything else, but near things are more related than distant things. I'm not even gonna say who said this. You don't have to. You can just put this up, and everyone will know who said that. I'm not even gonna say it. Anyway, when you make this notion of spatial data explicit, this distance encoding, people call it a weights matrix, and it's the foundation of spatial models. Whenever you use space in a model, you see it's called a weights matrix. When you have a weights matrix, you can do cool stuff like geographically weighted regressions. You can do things like feature engineering. These are also called data borrowing. And a great example of this, it's like a 3-hour long tutorial. It's the SciPy tutorial in 2018 on an introduction to geospatial data analysis. I've linked the GitHub here that you can copy it out or email me later and see what's available. It's an amazing course, and they actually show you how to do some of these things as well as what are called kernel regressions. But they all rely on this notion, this thing that only spatial data has, this weights matrix, this link between all spatial data. All right, but I think so. There's more to it than that, and this is the last. I think the last bit. There's also something called there's an emerging field in data learning or in machine learning and artificial intelligence called causal inference. It's been put out by a guy named Judea Pearl. It's been worked on since the 80s. And just so you know, causal inference is this idea that to arrive at a conclusion, causal inference is to arrive at a conclusion using a model that systematizes your data and your assumptions about causal interventions. That is, well, what if we had done things differently? How would it have changed our effect? About counterfactuals, I'm sorry, that's a counterfactual. What if we had done things differently? Causal interventions are, what if we did this? How would it, if we can do A, B, or C, how will it affect the outcome? A counterfactual is thinking about things in the past. What if we had not done these things? How would stuff have changed? And you can also talk about indirect effects. And Judea Pearl, he won the Turing Prize a while back for his work in this area. The Turing Prize, if you don't know, is like the Nobel Prize for computer science. He runs a blog out of UCLA, and this was one of his causal graphs. It's a way that he's developed how to reason causally, and he actually is talking about COVID. So I was like, well, I gotta put it in. And here you can see, you have this idea where because we have different transmission rates based on race and age or death, right? Different rates of death based on things like race and age. you can begin to build a causal model about how you think transmission works. And what he's done is he's created a, he's created a causal model. He's created a coherent mathematical foundation for analyzing those models. So once you build a model, you can use this it's called the do calculus. It's all about how do we intervene in the world? Can we model potential outcomes of our interventions? And so this is what he's known for. And this, of course, everyone's trying to put these into computers now. So what we're going to talk in, so the last bit, let's see. It's about confounding variables. So I wanted to define this before we move forwards, because I wanted to show you how spatial data and confounding variables can be related to each other in causal inference. So a confounding variable is a variable that affects both the independent and dependent variables in a model. Now, don't worry if you don't quite get that. Hopefully, it'll be clear here. So there is a clear correlation between ice cream sales and the number of shark attacks. And if you didn't know anything about the world, if you saw that these two things were correlated, you might begin wondering, oh gosh, what is it? Is there a couple of sharks that have started selling ice cream, or to lure people to the coast? Well, of course, everybody, that's clearly not the case. What it is there's a confounding variable. It's the time. It's summer. Summer is an unmeasured variable, something that we didn't include in our initial model, that influences both sales of ice cream and shark attacks, right? Summer, more people are at the beach. It's hotter, and so people are buying ice cream. Those two things, the first two correlated variables, are actually not related at all. And if you include summer in your model, if you include time in your model, that correlation actually disappears. And you didn't even have, it disappears. Here, I've got a couple more. This is a good one. Ministers' salaries and the price of vodka are actually correlated, right? You might think, oh gosh, what's going on here? I'm not going to say. What's actually going on is location, right? It's this urban and rural split. Ministers who live in rural areas are paid less, but the price of vodka is also less in rural areas. I mean, if you've ever, bought a beer in Chicago, it's clear that, $12 for an IPA or whatever, right? By including location, the confounding variable, you remove these spurious correlations that might have tripped you up. Got one last one. This is kind of fun. The number of Waffle Houses are actually correlated with the divorce rate. And no, it has nothing to do with, well, I'm not going to go anywhere. What that actually has to do with is that they're both linked to the South. So there are more Waffle Houses in the South. I think they're only in the South. But divorce rates just tend to be higher in the South. It has nothing to do with the number of Waffle Houses. But if we include the region variable in our models, we'll never run across these spurious correlations between. We'll never have to even think about potential causal reasons for how Waffle Houses cause divorce. Now, of course, those are kind of simple and kind of goofy examples, but in an actual practice, when you're trying to build a model, when you're trying to model solution space, it can be very difficult to recognize and account for every relevant causal mechanism in that model. And this is where, so there's another book I've been reading, Statistical Rethinking. This is what kind of put it all together for me. This is how I started thinking about why spatial data is so important and how it can be used in these like cutting edge machine learning techniques or artificial intelligence techniques. Location can mitigate spurious correlations. So we kind of saw that in terms of the minister and the price of vodka, even in the Waffle House Southern, the difference in that second thing. Given Tobler's law, location acts as a proxy for all the things that you haven't measured in your model. If you include location, because things that are closer together experience the same sorts of causal factors, then their distance, because they're close together, all the unknown or unmeasured confounding variables that you were unable to measure, that you couldn't think about, that otherwise affect the model, are accounted for. They're actually, you add those variables into the model by including location, even when you don't know what they might be, because location location is a proxy for everything else that you didn't consider, given Tobler's law. This is like the beast mode of that. This is called Gaussian process regression. It's Bayesian data or machine learning. this is something that I don't know, one day, maybe in years, I will be able to do. But at this point, yeah, I just wanted to show you this is kind of how it goes. And if you look for the spatial element, you can find it. It's on the fourth line. It's dij. It's the distance from one observation I to another j. So there you go. You plug in spatial data right there, and you get all of this really cool stuff in your models. Spatial data's power kind of just gets released. Yeah, anyway. All right, at the last one. I have no idea how my time is going. I forgot to, I have no watch. I have no, anyway. This is the last slide, I think. So yeah, here's, if you were to model this, if you're going to map the solution space, how would you go about doing it? What's the takeaway from this whole rambling discussion? Well, the first is to explore the problem space. You know, you look at a map to see what obstacles are in the way of your destination and plan ways to overcome them. This is the exploratory data analysis phase. But then you move beyond that and you begin to represent the problem that you have. You begin to represent your question as a structural causal model. You begin to put in all the assumptions and the data that you have and want to know about that you think will answer the question you have. And then you build a model that uses spatial data to mitigate the effects of any confounding variables that you didn't think about when you built your initial model. And then instead of mapping the problem space, you map the solution space. You take the output of the model you created and you map that. And ideally, when you show those, when you show the outcome of this of the model, it will begin to help answer the question that you had rather than simply redisplay the data that caused you to have the question in the first place. And yeah, just so you know, I'm not putting, I got to put my money where my mouth is. I and a number of other people, Dr. Brittany Wood and Mary Grace McClellan from DEP, we're going to put together a spatial data analysis blog. You can find it at terramodern.github.io. It's gonna attempt to do this sort of thing. Certainly not at this level. Please don't think that I could do the beast mode stuff right now, or any of us could, or we will be able to at one point. I promise. Right now, it's very basic. It's just actually a blog about how to set up a blog on GitHub, because we wanted to empower other people to kind of do the same thing. But in the future, we're going to be creating posts that show you how to walk through spatial data analysis, explain the concepts, and use free and open source tools to answer questions that are important to us and hopefully to you, and at least give you a way to answer questions yourself. So yeah, this is the plug for something moving forwards. And that is everything, I think. Is that my last slide? Yeah. How did I do on time?
Good. You got about 15 minutes.
Really?
Yeah, you did great. So if anyone has any questions, please type them in the question box. Phil, did you want to put up your contact information while we're waiting for questions to come in?
Oh, sure. Oh yeah, that's one thing you didn't do. Here we go. I'm just gonna put it. Can you see that, Janelle?
Yeah, I can see it.
Okay. Kind of rough, but if you go there, my GitHub account, let's see. I should have put all, I'm sorry, I didn't put this up. It's just, and if actually, if you go to terramodern.github in the blog post, you can find links to my GitHub and LinkedIn and email and all that kind of stuff. So.
Okay, so we do have one question.
Awesome.
Do you think we should include a spatial component to all statistical problems?
That is a really good question. I think to the extent that to the extent that the problem has a spatial component, I think it is certainly worth looking at, because clearly, space, the potential for including location in your data or in your model is is to mitigate these other factors. It's to account for all of the things that you didn't measure. And so it's certainly possible that you could be measuring relationships or trying to explain why things are occurring, and those explanations aren't affected by any of the similarities that are occurring in a similar location. So certainly, I'm not going to say that every causal, every model is going to require spatial data for it to be correct or for it to be the most accurate it could be, I suppose. But I think it's definitely worth, it should certainly be considered in the exploratory data analysis phase, I would say. That it's certainly worth looking at early on to see if those effects of the surrounding area do have any kind of play in the results of your analysis later on. And if they don't, it's fine, at least you checked for it. Yeah, so I think that's what I would say. I always think whenever I try and think of non-spatial data, I tend to think of like financial data or the stock market. But of course, even the stock market, you can compare the New York index to the Nikkei in Tokyo or the FTSE in London, right? And you can imagine that you can consider different trading strategies or different governmental objectives or policies that occur in those areas that would be accounted for by just simply including their location. Would it be useful? That's another question, but it would be worth looking into, I suppose. It's a long answer to a short question.
No, that's great. So let's see, we have a follow-up question, I think. So what did you use to decide your risk of visiting your family?
Just guilt, really. No. Yeah, honestly, I haven't been able to answer that question, and I feel like it's something that everyone has had to worry about. It's like whenever I go to Publix, I think, God, is this, is groceries this week the thing that's gonna like give me COVID? I don't know. I think that's the thing. That's what brought out my ire, I suppose, is that it's such an important question for so many of us. And I mean, I'm not gonna, right? I'm in good health. I'm able to stay at home and work. I do not have any of the, I think my like chances of dying from COVID are like 0.002 or something like that. So it's not even something that perhaps I don't need to worry about. But certainly I recognize that there are lots of other people for whom these risks are very real. And yeah, I was just struck by how clearly it's made public that we need to weigh these risks of going out, but then we're never given any information or any sort of even kind of rule of thumb to outside of what is obvious common sense, something that no one needed to tell me in the first place. No one gives you a rule of thumb on how to weigh those things. So yeah, I mean, yeah, I'm gonna say guilt at this point, and I gotta see everybody. But yeah, so this is just going by my gut.
I did see that someone had created an application where you can calculate your risk, but it doesn't seem to be very far along.
Really? Okay. Yeah, see, that's the kind of stuff, and I wanted to, I don't know what I was asking for. I still am not sure what I was wanting to see when I looked at the dashboard. You hear so much of all the Johns Hopkins stuff, and it is the place of record for COVID counts around the world. And so I was, to go there and to just still be at square one in terms of answering my questions. I mean, maybe that's the wrong place to look for questions or to look for answers. But then I guess, I don't know, where else can you go? Anyway.
So do you think that dashboards should really be displaying more of the solutions than the actual raw data? Would you yes. Lift your bias against dashboards if that was the case?
Yes, I think so, actually. So actually, yeah, so for instance, let me go. Can you still see my screen? I'm not sure.
Yes.
Okay. Just going to go back to it's here, it's this information where you can, because I was wondering, well, maybe if I'm not the person for this data, who is the person for this data? I was thinking if I was directing TMH, or if I was directing TMH, would this data be useful to me? And I was thinking, we have the number of staffed beds, but that's not really important. What I need to know is the number of staff beds today, the number of nurses and doctors who can staff those beds, right? You might as well put the number of floors in TMH, right? I mean, that's not going to change either, and it doesn't really help me any to determine, capacity at the hospital or any of those. I mean, number of beds is clearly more important than that. But it was just, I don't know, the total population of Leon County. I just look at the things on the bottom, and they're given with such precision. The county fatality rate to 2 decimal places. And I don't, none of this doesn't answer any questions that I certainly have. And I guess I was wondering, just if I know that the vast majority of people in Leon County are non-Hispanic, like, why is that information important? Like, what I want to know is, are ambulances in areas with low income and high areas of low income and people who are socially isolated, or socially vulnerable, how much more likely are they going to get the virus? Or, where are the hotspots today? And how are they, being influenced by demographics like age or socioeconomic status or that sort of thing? Yeah, but I think if I could see dashboards that had clear, and again, that's why I want to say clearly not all dashboards are only displaying problem space. I think the Johns Hopkins one is, but I would imagine if I'm the hospital president, I probably have a much more narrowly focused dashboard that, of course, I'm not going to share with the public. Although honestly, I mean, that's valuable information. Certainly, that influences my risks, right? Am I willing to go to the rock gym if we're at 99% ICU bed capacity? No. If we're at 2% capacity, and I know that I would have 3 medical staff taking care of me if I fell sick, maybe. Is that a bad choice? I don't know, but it would certainly play into my decisions. So yeah. Sorry, I'm just rambling at this point.
I think you make a good point that's something we all need to think about as the demand for dashboard grows. Are we just displaying data we already know? Or are we displaying data that's actually giving us information that we didn't already know? A lot of data is correlated with the density of population. So if you plot that on the map, what more are you really deriving from that data?
Yeah, there's a really good
hotspot was going to be in a dense urban area.
Yeah, exactly. I mean, one of the things that kind of made me chuckle was in the healthcare facts here. They have Medicare, how many people are on Medicare, or the percentage of people on Medicare, and they're all population above 65. And it's like, well, of course they are. That's what Medicare is for. You're not even telling me anything I didn't know. Anyway.
Okay, so we have a new question that came in. How do you think about the scale of spatial data that you include in your modeling for its influence and causality? Does larger versus smaller scale data lead to capturing more or less confounding variables?
That's a great question. There was a paper that I read in preparation for this, or one of them. I almost wanted to post a link to this. Maybe I will. If you email me, I can send you something where he actually talks about this. Is one of the big questions, and it actually is something that separates. It's another thing. It does separate spatial data from other data in terms of how difficult it is to collect information. I think, if I'm remembering correctly in the paper, he mentions it's a guy named Luke Anslin. He's the one who came up with local indicators of spatial autocorrelation. He's this huge name. Now he's at the University of Chicago. He built, there's an application, a spatial analysis program called Geoda that he created and has built, and PySal is a Python spatial analysis library that was very much a collaboration between him and another big name. Anyway, he mentions how the data that we gather should be at a scale that makes sense for the problem we're trying to answer. So, you can imagine if we're talking about, if we're trying to build a model at the level of counties or perhaps at the level of the state, clearly we're going to need, the effects that how the different important variables are interrelated are going to play a different role at that level. If we need answers if we need answers about, let me think how to say this. if we have questions that can be answered at the state level, you know, broad policy decisions, whether or not all of Miami should be shut down, that sort of question, and not simply, you know, should one block be quarantined because there's been an outbreak, or like some of the people I know, you know, they're one class in preschool, they had one person with COVID, so the whole place needed to be quarantined. If we're thinking at such a much larger scale, you can imagine the kinds of spatial data you gather should be at the same scale as the problem you're trying to solve. However, I think what's actually kind of cool about spatial data is that it can be aggregated. You know, if you gather things at a very fine-grained spatial level, you can always clump them together. You can always join them together into larger pieces that make sense at a higher scale. It's much more difficult to go the other way. It's a really interesting problem to go backwards, where you have, you know, things like you have a census tract and you want to figure out where do the people actually live in the census tract. You need to talk to Dr. Georgiana Strode about that. She's the expert. But yeah, I think the level of data should be at the same level as the question you're answering, or presumably the answers that you believe are feasible, if that makes any sense at all.
Yeah, absolutely. I think you answered that question great. So this is a last call for questions. It's your time to pick Phil's brain. We'll give it a couple of minutes, see if anyone comes in with a question.
I can't believe I went through that so quickly. I apologize if I just blew through stuff. Anyway.
Well, that's a good segue into me reminding everyone that we're recording all of these presentations, and we will be posting them on our YouTube channel shortly. So you can revisit this and watch it many, many times over.
Oh crap, that's gonna be on YouTube now. Never mind.
That's right.
Can you edit that out? Edit that out.
It's on there forever. Okay, well, it looks like we don't have any more questions. I just want to thank you, Phil, for presenting. I always enjoy your presentations. And
thank you everybody for coming. Sorry.
No, I'm sorry.
I just wanted to say thanks for everybody for showing up. I really appreciate it.
And I will say you got quite a lot of accolades in the question box.
Oh, okay. I can't see any of this. Anyway, well, thank you. Yeah, hopefully you'll follow us, Terra Modern, on our blog, and you'll see what we'll do, and you'll be able to do the same sort of things. Our goal is to empower everybody to do the kinds of impressive stuff that I know spatial data is capable of. Anyway.
All right, great. Well, thank you, everybody. And the next presentation is going to be after lunch at 1 o'clock. All right, thanks, Phil.
All right, bye.
Bye.